In the meantime, we'll go through some introductions and how the Q&A works. I'm Julie Moreira. I'm a Principal System Design Engineer at Teledyne FLIR OEM. I'm thrilled to be here to talk with you today about computational imaging and midwave infrared sensor optimization. And joining me is my colleague.
Thanks, Julie. Hi, everyone. My name is Art Stout. I'm the Director of Product Management for AI Solutions at Teledyne FLIR OEM. I'm excited to dive into today's topic with all of you. We're here to answer your questions throughout the entire session. If you have any thoughts, insights, or questions, drop them into the forum below, and we'll make sure to answer them. A recording of this session will be shared with the group as well. All right, let's jump right in.
I'll be presenting the first half of this talk on midwave infrared size, weight, and power and cost optimization, which we also call SWaP-C. So theoretically, decreasing pixel pitch enables a reduction in size, weight, and cost of our camera systems. For wide field of view imaging applications, we typically have faster f numbers to begin with and fixed focal length lenses. So further reduction in f number required by the smaller pixel pitches is countered by the focal length reduction and is often worthwhile for SWaP. For narrow field of view applications required for long-range imaging, for example, more complex continuous zoom optics with slower f numbers are employed. More so in this case than in the fixed zoom scenario case, the system-level trades should be considered before just choosing the smallest pixel pitch available on the market. The pixel pitch selection is less straightforward when considering the impact on the overall system's size, weight, and cost. In this talk, we're going to be focusing on infrared cameras at the system level. From readout integrated circuits, detectors, and cryocoolers to midwave infrared and longwave infrared thermal camera modules, optics, and advanced signal processing and AI, Teledyne FLIR is the world's only vertically integrated infrared hardware and perception stack provider. So Teledyne FLIR designs and manufactures infrared camera sensors and the associated optics in pretty high volumes, selling complete integrated imaging camera modules with each component designed to optimize system, SWaP-C, and performance. So this vertical integration provides us with a unique perspective on the relationship between component specifications and overall IR system optimization. For example, without considering the end system, you could find yourself in the scenario of a well-designed, miniaturized camera core with a gigantic, complex, and expensive optic mated to it. So we'll walk through an example of a cooled midwave infrared camera system representative of our Neutrino Integrated Solutions, or NIS series, where midwave camera cores with multiple pixel pitch options are paired with a variety of continuous zoom lens options. My colleague Art will then have a follow-on session discussing the next layer of vertical integration, our offerings on advanced signal processing capabilities. Let's begin with the basics of why reducing pixel pitch theoretically reduces the size of your camera. The figure illustrates that for a given number of pixels on target, pixel resolution, and field of view, shrinking the pixel pitch or the pixel size can theoretically reduce your system size. Obviously, the pixel array or sensor size itself is reduced proportionally, which can reduce the width and height of your camera core, but also for a given resolution and field of view, the effective focal length required of the lens or the cold-chilled aperture is also reduced proportionally, which can reduce the length of your camera core and optic. As alluded to, when developing midwave infrared systems, that include continuous zoom lenses, there are additional factors to consider that diminish or may even overcome this theoretical pixel pitch reduction benefit. Integrators must optimize the complete system performance, design complication, cost, and size, especially when continuous zoom lenses dominate many of these SWaP-C metrics. So let's consider some factors that might offset the pixel pitch reduction benefit. So let's start with sensitivity. Smaller pixels have less active area to collect photon flux, which reduces our signal-to-noise ratio. To counter this, smaller pixel sizes require proportionally faster f numbers to achieve similar sensitivities. This means the system diameter, which is driven by the front optical element or entrance aperture, is the same as or slightly larger than the larger pixel systems of the same sensitivity. Let's talk about spatial resolution. So similarly, smaller pixels also require a faster f number to achieve the same spatial resolution or maintain the ability to resolve targets. So faster f numbers are notably more expensive and difficult to manufacture, and near diffraction limited performance is prohibitively costly and are unachievable in certain cases. So on to optical tolerances. Faster f numbers require tighter optical design tolerances, complicating the design and manufacturing processes. Size, weight, and cost may all be negatively impacted. A good rule of thumb for the f number cliff at which the complexity and cost increases for continuous zoom lenses is f numbers below f3. Continuing on to other performance impacts, dynamic range. Smaller pixels have a reduction in charge storage or well capacity, which reduces the dynamic range, impacting system performance. Readout integrated circuitry is required to become more complex to handle these higher density interconnects as the pixels shrink and provide similar capacities within smaller unit cells. Furthermore, on sensor performance, achieving detector performance with smaller pixels is notably more challenging. Smaller pixels can have reduced quantum efficiencies. That's the efficiency of converting photons to electrons. This is especially true with strain layer superlattice detector structures, which are readily employed in our industry to enable high operating temperatures. So smaller pixels suffer from an increase in dark current due to surface defects and sidewall leakage, increasing the system noise, limiting operation at those higher temperatures I just referred to. Higher temperature operation is beneficial for power, readiness time, and reliability of our coolers. So similarly, isolation of smaller pixels is more challenging. As the pitch to diffusion length ratio decreases, the fabrication processes become more challenging. The resulting pixel-to-pixel crosstalk is often degraded. So spatial crosstalk and residual fixed pattern noise impact range performance. They're not typically well captured in high-level specification data sheets, but that pixel-to-pixel crosstalk further degrades system MTF and overall performance. Complex material engineering and mitigation strategies are required to overcome some of these issues I just mentioned. So there's a high dependency on the maturity of the small pixel processes as it relates to the actual performance beyond theory. So the required complexity on the readout and the detector we just referred to, on the design, the manufacturing process to achieve similar performance to those larger pixel arrays often offset the increased die per wafer cost reduction we might imagine. All right, so now I'm going to walk through an example where smaller pixel pitch does not translate to SWaP-C advantages for an infrared system. The table shown here provides a real-world example comparing 3 system designs derived from a specification of a typical 10x continuous zoom lens. In this example, sampling and sensitivity are expected to remain the same for each option. So we're expecting the same application and being able to achieve the desired performance for that application and needs for that application, but with 3 different pixel pitches. So the pixel pitch drives F number requirements. Smaller pixel pitch, faster F number. As shown earlier, for an equivalent instantaneous field of view for each of the systems, the smaller pixel pitch equates to reduced effective focal length. That would seem like a reduction in the length of the overall system, right? We'll take a look down at the number of elements first. As for complex zoom lenses, the number of optical elements required for faster F numbers increases. Optical aberrations must be controlled across a larger solid angle in the optic design for faster F numbers, making them more difficult to correct. So the performance is impacted and you need more elements to handle that. As shown on the next row down, the optics systems dimensions row, the physical length of the overall optic is actually shorter for the large pitch, slow F number system with the longer effective focal length than it is for the small pitch, faster F number system with shorter effective focal length. In addition, the small pitch, faster F number system results in a notable increase in weight because the increase in number, size, thickness, and curvature of the optical elements required to meet the tighter control over tolerances needed for the increased ray bending of a faster F number optic outweigh the advantages of the smaller pitch. So finally, the small pitch, faster f-number optic cost is notably higher than the large pitch, slow f-number optic due to both the design and manufacturing processes required to accommodate the more challenging corrections and tighter tolerances required. So you can imagine more complex alignment procedures and such. In short, size, weight, and cost of a continuous zoom optic increase as the pixel pitch decreases from 5 microns to 8 microns to from 15 microns to 8 to 5 microns in this particular example. So now we're moving on to overall system cost. The system level cost includes both the optics and the camera module cost, which includes the die, wafer, cryocooler, and other subcomponent cost inputs to that camera module cost. As shown in the figure, the system level cost decreases with pixel pitch. For this particular example of a 10x continuous zoom optic and accounting for focal plane array costs, the 8 micron pixel pitch provides system level cost savings when compared to the 5 and the 15 micron pixel pitch respectively. In simplest terms, the system level costs hit a point of diminishing returns and become more costly as the smallest pixel sensors are utilized due to optic cost and small pixel focal plane array maturity. In addition to the cost, size, and weight advantage we just discussed for larger pixel pitch systems, we have detection, recognition, and identification performance to consider. DRI are criteria describing the effective range of an infrared camera. Teledyne FLIR uses DRI probabilities modeled using NVIPM, which is an industry standard passive sensor modeling tool. V50, or the measured task difficulty, is the targeting task performance, or TTP metric value required to provide the user with a 50% probability of accomplishing a given task. These criteria give a 50% probability of an observer discriminating an object to a detection, recognition, or identification level. For identification task, the observer must correctly identify each target from the target set. For recognition, the observer must identify the correct class of the target, such as a military vehicle or handheld object. And finally, for detection, the observer must correctly just detect that there's a target in the scene. Continuing the 10x zoom lens design example, the performance of 3 systems can be modeled. For these results, a target critical dimension of 3.1 meters and a target temperature variation of 4 Kelvin, so reasonable inputs for an NVIPM model, were used. A typical degradation and optical aberration MTF for the F18, F29, and F55 optics were used. A conservative reduction in signal to noise was used for the 5 micron, 8 micron, and 15 micron pixel pitch systems. And I held detector diffusion MTF constant, which gives an unrealistic advantage to the small pitch system. And all other parameters were held equal, so target, atmosphere, camera spectral transmission, display, etc. So the distances at which there's a 50% probability of achieving the task for the V50 measured task difficulties, in this example, 2 for detection, 9 for recognition, and 13 for identification were used. The model data indicates that the 5 micron pixel pitch has a modest range advantage on the order of 10% for the comparable 8 micron and 5 micron pitch systems. When continuous zoom lens cost and IR system level cost and performance are examined for our 5, 8, and 15 micron pixel pitch systems in this example, SWaP-C and performance are not optimized by pixel pitch minimization. Smaller pixels require faster f-number, which increases the optics complexity, size, weight, and cost. The IR camera module cost, which includes wafer, cryocooler, and other subcomponents, is also not necessarily minimized with smaller pixels. As shown in the example, the IR system level cost is minimized at 8 microns, not at the smallest 5 micron pixel pitch. When the comparison example is extended to include performance, the largest pixel system of 15 microns is shown to have a slightly improved DRI range. In summary, integrators and users may find for the current industry offerings, the push for ever smaller pixel pitches may reach a point of diminishing returns for key system requirements, including SWaP-C and performance. And that wraps up the SWaP-C optimization talk, and my colleague Art will walk you through the next section.
We're going to be discussing our image signal processing on our AI algorithms. Our Prism software libraries consist of these three main categories: image signal processing, perception, and autonomy. First up is the tone mapping. This is our 16 to 8-bit tone mapping algorithms. We have a variety of different approaches. Again, it's highly scene dependent. We have super resolution, which is a patented approach for upsampling imagery. We're going to be showing 640 upsampled to 1280 by 1024. We have a turbulence mitigation filter, which is very useful for ground ISR for midwave systems. And we're going to also then talk about our haze penetration filter, which deals with obscurance and things like that. And then we'll finish up with a discussion around our object detection and the various models that we provide. So with the advance of all these software capabilities, we needed the necessary hardware to run these very computationally demanding algorithms. Unfortunately, in the marketplace today, because of the advances in AI and the processors to run them, the industry has developed a set of very advanced hardware. We focus support around Qualcomm hardware, and we've introduced what's called the FLIR AVP, or Advanced Video Processor. This is a Qualcomm 8550 SOM-based product. This is a 50 trillion operations per second class processor on a 4-nanometer node, which offers exceptional power efficiency. We also support the RB5, which is a very popular SoC that's deployed in many, many drones. And then we also support NVIDIA and its Orin family, the Orin Nano, NX, and AGX. And each has unique, important capabilities in terms of overall power and the development environment that both our customers can develop on. Within the Prism ISP functionality, we've got various AGC algorithms, super resolution, turbulence mitigation, image fusion, electronic stabilization, and haze penetration. Within the Prism AI family of capabilities, we have object detection, a fine-grained classifier, which is the ability to not only do a generalized class detection and provide a label and confidence score, but a fine-grained classifier then enables us to identify things by sort of make and model. MTI is our motion target indication. This enables us to launch the tracking of targets before there are enough pixels on target. We have a multi-object tracker, which is a CNN or neural network-based multi-object tracker. Our single object tracker is a correlation tracker, which runs on a single CPU core. And then we'll talk about our fusion and our IR seeker application. And the other components are just tools that we use to help developers. So within the Prism ISP library, the first one that we're offering is what we call super resolution. So this is a patented approach that reduces aliasing and actually improves MTF by 75%. So it's a fairly dramatic improvement in image quality. In this video sequence, you'll notice the scene will go back and forth between super resolution applied and not applied. This is a boson 640, a boson plus 640 with 20 millikelvin, and you can see here the palm fronds here. That's the detail that I'd like you to focus on. And you can see that as we switch back to the native boson output, which is excellent, you can see just the improvement in the fine details in this area specifically, but throughout the image, you can see just a fairly dramatic improvement. And again, this algorithm runs on the Qualcomm or NVIDIA hardware. It does introduce some latency, so we'd have to consult with you as to exactly what your system requirements are with regards to that. But you'll also then running our ISP, also our denoise capabilities, reducing the NE delta T an additional about 40%. Turbulence mitigation deals with the effects of the turbulent atmosphere. When you get ground heating effects, the air currents, you get air currents, which those air currents refract the infrared energy between the target emitting the energy and the camera receiving that. And you will get this, and that's common across all the spectrum, whether it's the visible spectrum or whether it's in the infrared spectrum. And when you're looking at long-range applications, the ability to remove the turbulence. So what we're basically doing is we are basically putting pixels back where they belong without the effect of turbulence. And if this is an input into a perception stack or an object detector, you can see that in the video that we show here that we're not losing some of the temporal consideration of the temporal detail. So you get the arm separations and such. And so the quality of the perception or running this input into our AI stack is much enhanced. Similar to turbulence is obscurance, so rain, snow, fog, those kinds of things. And we have developed a turbulence mitigation, a haze penetration filter that recovers the MTF and provides some of the details. It's basically an image reconstruction approach. And you can notice here the power lines in the tower over here are not really visible, and they are over here. So again, we're able to reconstruct the image and remove some of the effects of turbulence. And so it's a very effective filter, again, for long-range applications where weather or obscurance may create problems. And again, performance of any sort of AI or ATR with this filter applied will greatly improve the performance of your object detectors and the ability to track targets. Image stabilization, this is electronic image stabilization. And so for cameras that are mounted on masts, on moving targets and such like this, stabilization is a critical thing. And it's a cost-effective approach versus doing some more active type of stabilization. So as you get into longer and longer focal lengths, the effects of a vibration on the platform are going to be seen in the image, and it's something the operators would like to see removed. The next part of our ISP is our noise reduction. Since we can't compress noise, the ability to reduce noise vastly improves the bit rate. And so here in the top frame, you see a boson put into low gain mode, which outputs the most dynamic range, but a higher any delta T. So that's a good sort of reference or source data for our noise reduction filter. That in this second frame, we're super resolving as well. And you can see the tremendous improvement in the image quality. And then you see, as reference, the boson 640 just simply upsampled to the same resolution of 960. And we're sort of approaching the image quality of a more expensive sensor with a 320 camera in this case. And of course, you could apply the same principle or the same logic to a 640 upsampled to a 1280 camera. And the real advantage then in the compression beyond just image quality is the reduction of bit rate. For many systems, there's always an RF link. So a lot of drone payloads and a lot of applications will transmit the video through an RF channel that typically has a very limited amount of bit rate, and you can basically set quality rates based on the bit rate available. So this gives you the opportunity to transmit the highest image quality at the lowest bit rate. And all these algorithms run in real time. So on the 8550 particularly, and the Orin products, these will run at frame rate. So we have a stack running Denoise, super resolution, our advanced dynamic ADE, AGC algorithm, and perception. And all of that is running at frame rate or faster than 30 hertz. The next up is our image fusion filters. We have a variety of different image fusion capabilities. I point this one out. This is our patented MSX. So we take the thermal image and then we overlay the visible, but we apply a high frequency filter to the visible light image and only extract edge details, which we then lay over on the thermal image so that you get a very, very high fidelity thermal image with some of the visible light information displayed without too much of the typical fusion confusion around, the way you map a color visible light image onto a thermal monochrome image. And so here we're able to read things like license plates. You can imagine in a drone payload, the ability to go into a hazmat situation and read sort of chemical signs or other sort of critically important visible light data and just focus on the thermal, for operator consumption. We'll now then shift over to our perception software. So Prism AI is a series of models, and they're application-specific models. So today we have 5 models. I'm going to show examples of 2 of those models. This is our air-to-ground model. There are 5 classes. And again, this runs at frame rate. Inference on the 8550 takes around 3 or 4 milliseconds. So this gives you the ability to provide systems that can automatically detect, label, and start tracking multiple targets. And the next model I'm going to show is our Counter-UAS, counter-drone model. So this is a model that was trained on 2 classes, a generalized UAV model and birds. And this allows us to disregard the bird detection so that from a systems point of view, the output of this is just the drone detections with their confidence and with the tracking outputs that are necessary to drive the pan and tilt or any sort of countermeasure that's going to be directed at these drones. And this model has very reliable drone detection. It's obviously dependent on the optic and the resolution of the sensors, but we get high confidence drone detections with about 10 by 10 pixels on target. As Julie had talked about DRI, sort of the same sort of approach can be applied to machine learning or AI, where a generalized object detector can do a detection. So with the minimum amount of targets, it can make a class distinction of car, truck, ship, person, that type of thing. And then as you go down and the target starts to get closer and you get more pixels on target, with proper training, meaning the generation of data, the labeling of that data, and then the model training, with that additional detail, you can start to then get outputs about the specific class, so a military vehicle, civilian vehicle, that sort of thing. And then ultimately, with enough additional pixels on target, and again, with the training having been performed correctly, you can actually do make and model. So we now have models that can distinguish military vehicles by make and model. And that's very important in some of the targeting applications or autonomous seeker applications that are under development. And here's an example of a fine-grained classifier. As the video is moving through, you'll notice the labels here. We have the vehicle at 91% confidence. It's a military vehicle. At 100% confidence, it's in a main battle tank. And so this is kind of a unique capability to do this in the thermal spectrum, because again, the data sets available to do this type of training are very difficult to get. And much of the model training here was done on synthetic data where no real data was available. And we continue to build out this tool and this capability to be able to provide this capability to customers who need this kind of capability in both spectrums, visible and thermal. And that's what we have for you. Thank you very much for your time.
Thank you.
Thank you.